In this lecture, you will be introduced to how energy demands can be modeled in osmosis. On this slide, the overall structure of this course and its modules is presented. These lectures are used to guide you through all the basic necessary steps to understand the elements of an energy system and how they can be represented in an osmosis model. Please keep in mind that during this training our objective is the creation of a country model. Therefore, some information will be provided in relation to a country-level model. However, there are no restrictions to the definition of model boundaries in osmosis. During this lecture, you will be guided through the basic reasoning and approaches of defining energy demands in osmosis. In the first section, a general introduction to characteristics and types of energy demands are given. The second section elaborates on how to implement energy demands in osmosis. So, let's start with the general characteristics and types of energy demands. In previous modules, we have been talking about reference energy systems, RES, as shown on this slide. Energy demands are commonly represented at the very right of an RES, as marked by the black box. This can be different types of electricity demand, but also demands for water or food. But let's look a bit more precisely on where energy demands originate from. Because in the end, it is not the energy commodity itself that we are demanding, but the service that this commodity is used for. In everyday life, in a household, energy demands arise for cooking, heating, and cooling, and many more appliances. But not only at the household level energy demands occur. In all sectors of the economy, energy is needed to facilitate certain services. For example, in the commercial sector for cooling, in the transport sector to move vehicles, and in the agricultural sector to pump water. In the graph on this slide, we have a set of different energy demands, shown in the bottom area. It is visible how they vary in different patterns over time. When summing them, we get the total demand and its variation as shown by the brown line in the upper half of the graph. The challenge in energy planning is that these patterns and the demanded quantities change over time. For example, because of population growth, new businesses coming up, or industries that disappear. To build energy systems planning models, these changes and their impact on the energy demand of the future need to be anticipated and estimated. The graph on this slide indicates how such demand forecast can look like. Both the forecasts consider to some extent the development of the past. A key purpose of modeling in osmosis is capacity expansion planning. As a starting point for this, we usually know the currently existing system capacity and how this is expected to develop over the time analyzed. This means we might know of power plants that are going to be installed in the next years, and by the technical lifetime we get an indication for how long the current power plants are going to produce. However, based on our demand projection, we can estimate how much capacity is needed in the analyzed period. And since the existing capacity is commonly reducing over time, as indicated in blue, where the demand is often increasing, indicated in green, there is a need to identify what technologies could be used to satisfy the demand. In osmosis, this can be done while considering technical, economic, and environmental constraints. To satisfy the expected demand in a reliable manner, it is necessary to always provide sufficient power generation capacities. This required capacity is indicated in red in the upper area of this graph. Therefore, the gap between the red graph at the top and the blue graph of the existing capacities at the bottom indicates how much new capacity is required at least to be able to satisfy the expected demand, shown in green. The analysis and therefore also the forecasting of demands can go down to a very detailed level, since within each sector the demand varies again between the different classes of consumers. For example, an urban household has a different demand pattern as a rural household, and among rural households the demand pattern will be affected depending if the household is grid connected or not. The task of energy planners is to ensure that all these varying demands of the different consumers are met at any point in time. This implies that also reserve capacities are in place in case of unforeseen events or outages of system components.